All right, so welcome everyone. Welcome back to CS196. This is our last lecture of the semester, so congratulations, all you guys made it through. I hope you learned a lot. I hope it was informative. Sammy and I had a lot of fun teaching the class this semester, and yeah, let's get right into it. So first of all, let's start with our objectives. So we're going to talk about shared state concurrency, the issues with shared state concurrency, mutexes, mutual exclusion, mutexes in Rust, and then finally we're going to end with some uses of concurrency. Really the main topic for today is trying to understand what shared state concurrency is and how mutexes help us solve that. And mutexes aren't just exclusive to Rust. This is a topic that you'll see in many other languages that allow for multi-threaded programming. All right, so from last lecture, also if you're just in, I'm going to keep pasting the code for the Kahoot into the chat. If Sammy's in there, he can probably paste it in for you too. Sammy isn't there, so we'll be doing a Kahoot today, obviously. All right, so from last lecture, so we learned about channels and thread communication through channels in the last lecture. So we focused on this because reading from the same memory leads to issues in concurrent programs, and we saw that with Sammy's example of the person trying to read from the ATM and ending up with more money than they should have because of how the threads communicated. And the use of channels in any programming language is similar to the idea of single ownership. So we know how ownership works in Rust, where each variable typically only has a single owner. So once a value is transferred down a channel, the thread should not access data anymore because it's passed off ownership to the new thread. By doing this, we prevent the errors that occur in concurrent programs where two threads access the same data and modify it at the same time. Communication by channel prevents different threads from needing to share memory. But what would this look like? So Rust is pretty unique in the sense that it has the idea of single ownership and the way it handles ownership. But a lot of other languages allow you to share memory. So Rust isn't blind to this idea, and it's aware that a lot of other programs are familiar with how to share memory and how to do this effectively. But let's see what it looks like in Rust and how we can utilize this in a different way to how we did last lecture. So let's talk about what shared state concurrency is, and it's this big block text here. So shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time. All right, so this sounds like bad news, but let's just go into why exactly this is bad news, or an example for this. So let's talk some issues with threads and accessing data, and this is a pretty good example for that. So this is some pseudocode. It's kind of like Rust-ish code. So we have a static global variable. So this global variable can be read by all threads. And we have a simple for loop from I, 0 to 10. Let's increase this by 1. All right, so 3 important steps take place when incrementing a variable. So the thread firstly reads the current value of the variable. The thread increments this value, and the thread writes this value to the variable. So whenever we're trying to do an incrementation like this, it isn't a one-liner thing. Several things happen in the same place. So if you do 33, you'll understand that when you increment a variable, you first have to read this into your memory, you'll increment the value, and then write it back. So 3 things happen, and this is why multi-threaded programming kind of fails when you have shared memory. So let's say we're reading here. Let's say we're going from 0 to 8, so that this fits here. So we're going to be reading here. It's pretty simple in a single-threaded program. We just go 1, 2, 3, 4, 5, 6, 7, 8, and this is done. We're going to pretend this says 8 here, not 10. And what I'm saying by meanwhile we're reading here is the value in thread 1 on this side is going to be the value after we increment. So whatever like the value of global variable is once we're past this line of code. And as you can see in a single-threaded program, it's pretty basic. Like we didn't really expect anything else to happen. This is going to be, I'm going to pointer up. This is going to give us value of 8 because we're incrementing 0 to 8. But now let's look at how this works with 2 threads. So now with 2 threads, let's say we're going from 0 to 4, not 0 to 5. So we're halving that value, and we're going to increment 4 times through these 2 threads. And again, we're reading here after we increment it. So whatever value you see here is the value after this thread has incremented it. So our goal, I guess, would be to still get the value of 8 at the end, except we're going to have double the speed because we have 2 threads incrementing at the same time. Unfortunately, that's not how it's always works. So let's see how this could work. So let's say so notice that we have this value here. Notice that we're in thread 1 now. So thread 1 doesn't really know what thread 2 is doing. It's not really aware of this at all. It's just doing its own thing independently, and we're not communicating with thread 2. So right now, thread 1 reads the value of global variable. Global variable is at 0, it increments it, and then saves it as 1. Pretty standard. Let's say thread 2 starts a few nanoseconds, microseconds after global variable. So when it reads the value here, the value's already been incremented to 1, like so. So it increments the value and saves it as 2. And this is what it looks like. This is kind of what we wanted to happen. Unfortunately, we don't know how the CPU allocates time to these processes. That is totally dependent on the scheduler, and there's no guarantee it's going to do it the way we want it to. Now let's look at thread 2. Thread 1 again. So thread 1 in our second iteration reads the global variable here. The value is 2 because it probably waited a couple nanoseconds, something happened. We incremented, and now it's 3 here. However, while it was incrementing this value here, thread 2 was also reading this in. So it read the value in, it got 2, incremented it, and got 3. And now, oh no, our thing's already broken. Because thread 1 and thread 2 access the same data at the same time, before thread 1 had a chance to write down this new value of 3, thread 2 had already started reading it. And I'm sure you can see where this is going. Let's say thread 2 starts earlier this time. It'll read the value of global variable as 3, increment it as 1. We get 4 here. Thread 5 might start a couple of nanoseconds afterwards. This is just one simulation of this. Gets 4, increments it, gets 5. Okay, so now we're offset again. We're not at the point where we want to be. We want to see 6 here. And now when we reach the final iteration, we have actually 3 or 4 different versions from this state of where we could be. For instance, if both threads access global variable at the same time, we can have them be at 6. It could be 6, 7, 7, 6. It could even be that thread 2 started before thread 1 even had a chance to increment itself. So it might be a 5 here. And this is obviously very, very bad. We have no idea what this code outputs. If we ran this 10, 20 times, we'll probably see different values for global variable every single time. And this is what we want. And this is where the idea of a mutex comes in. So let's talk about what a mutex is. So mutex is short for mutual exclusion. So mutexes solve our previous issue by only allowing one thread to access the data at any given time. So to access the data that is in a mutex, the thread must first ask for the mutex's lock. And the lock is the data structure that keeps track of who currently has exclusive access to the data. So essentially what happens is we lock our data with the mutex. Whoever has locked the mutex can access the data and read it freely. However, the other threads, when they want to try and read the data, when they try and get the mutex, they'll stop running. They'll block because only one person can have the mutex at any given time. And let's see this example with a conference analogy. And just so we don't lose, and so let's say we have a set of speakers like this, an audience here, and unfortunately only one microphone. And so we don't lose track of our initial goal problem, let's just label everything. So these are our threads here, the speakers, the mutex is our microphone, and the audience is our data. So the way this works is a single speaker can go to the microphone, and then they lock the microphone. Only they are allowed to use the microphone from now on. And they can speak to the audience, receive data from the audience. Essentially, only one person can interact with the data at this time. When the speaker is done, they unlock the mutex, go back, and a new speaker can come and access the data. The new speaker arrives, locks the mics, only they can use the mic, and they can speak. And they unlock it, and so on and so forth. By doing this, only one person is allowed to access the data at any given time. And this is great. This is exactly what we wanted. Unfortunately, mutexes are a little more complex than that. Let's say, for example, speaker 1 goes over here. He's talking to the audience, having a great time. But then he leaves and he takes the microphone with him. He forgot to unlock the mutex. Well, now what happens? Well, so the other threads here, they also want to speak. So they're just going to wait here for a bit. And they're just going to keep waiting and waiting. Just going to keep sitting there for a bit, a little longer. Wait, they're not going to get the mic ever. Because the mutex was never unlocked, they're never going to be free, and the code gets stuck into something we call deadlock. Okay, deadlock is a kind of scary sounding name, and for very good reason, because when your code deadlocks, it is stuck. It is never going to finish, and you're in this state where your code is frozen. It's very hard to debug. A lot of bad things happen. So let me define deadlocking for you. So deadlocking occurs when a thread forgets to unlock a mutex. Therefore, when other threads go to access the mutex, they block on it, and therefore the code can no longer progress. The reason this happens is because when someone locks a mutex, any other threads that reach that line of code will block automatically. They're going to block and wait for that person to let go of the mutex so someone else can take it. If that never happens, your code is never going to finish. So we get deadlock. So mutexes have two important rules. And you're probably wondering why, this seems pretty obvious, unlock it after you're done using it. But surprisingly, you'll see in a lot of complex multi-threaded programming that it isn't as obvious as it may seem. There might be several cases where you have to lock/unlock a mutex. You might have several mutexes in a given instance. The way different threads interact with these things is difficult to predict. So deadlocking isn't something that's a rare occurrence. You will see deadlocking very frequently when you're writing multi-threaded code. That's okay. We're going to talk about how Rust helps us avoid this. So with mutexes generally, there are two important rules. Firstly, you must attempt to acquire the lock before using the data. And secondly, when you finish using the data that the mutex protects, you must unlock the mutex so other threads can acquire the lock. So this is exactly what we're talking about. The mutex protects the data, and you need to have it to use the data. So as long as you have the mutex, nobody else can use it. And when you're done using it, you have to let go of the mutex. You have to unlock the mutex so other threads can acquire the lock and continue using the data, and the program can continue. So there's a lot of information there. Any questions about the mutex or any concept we covered previously? You can just drop it in the chat. All right, let's move on then to our Kahoot. So here's the Kahoot code. I'll paste it into the chat as well. I'll keep it open for one more minute, and then we can get right into the Kahoot. All right, I think everybody's in. If you're not in yet, you can just make a question in the Twitch chat, and I can paste the code in. So let's start with the Kahoot Concurrency 2. So shared memory concurrency is like all right, so this one had a lot of mixed responses. So let's go back to my slide from before. Jump all the way back, I guess. All right, so shared memory concurrency is like multiple ownership because multiple threads can access the same memory location at the same time. Yeah, so that's a definition. The way shared memory concurrency works is because the memory is shared between all the threads can read and write the same thing at the same time, which is why we have mutexes, so that we can protect data from being edited at inappropriate times. All right, next question. So what is mutex short for? Okay, so again, the first one's a little tricky. Mutable exclusive sounds pretty similar, but it stands for mutual exclusion. So most you got it correct, or a big chunk you got it correct. The name Mutex kind of like comes from the idea that only one person can access, or one thread can access data at the same time. So they're mutually exclusive. No two threads can access the same data at the same time. And therefore we get the word mutex, mutual exclusion. Just remember that's super important. This will come up a lot in later classes where you do parallel programming or more multi-threaded programming. So yeah, next question. What is deadlock? All right, great. So most of you got this correct. So deadlocking occurs when a mutex is locked, never unlocked, or it never unlocks because of a certain condition not being met. Therefore, all the other threads will hit the mutex, block, and then never complete because they can't move past that line of code until they require the mutex. So great, most of you guys got that correct. A big shift in the leaderboard there. Question 4, which of the options below can cause deadlock? All right, yeah, so most of you guys are correct. Again, there's 2 correct answers here. So if you forget to unlock a mutex, obviously when the other threads come to that mutex, they'll just block on the mutex, and they'll never finish. Similarly, if you lock a mutex that will never be unlocked, it's pretty similar to the first case where all the other threads will hit it and never finish, so your code will never finish. Unlocking mutex too early doesn't really matter. You might have issues with your data being edited when it shouldn't be edited, like in our first example. But if the code will still run, it'll be deadlocking. Finally, forget to unlock a mutex in a program with one thread. Doesn't matter because you don't even need a mutex in a single threaded program. If you lock a mutex, that code will just keep moving past. It doesn't stop on the line where the mutex is. The mutex is kind of like a barrier preventing other threads from passing that point. And we'll talk about that when we look at the actual code. But yeah, in a single threaded program, it doesn't matter whether you have a mutex or not. If you try to unlock an already unlocked mutex, you'll have undefined behavior, but it's not going to cause your code to deadlock. All right. I think we have one more for this round. Yeah. So true, false. You must attempt to acquire the lock before using the data. All right, great. You guys all got this correct. So yep, this is exactly what we're talking about. You have to attempt to acquire the lock before using the data. And why the word attempt is used instead of you must get the lock is because all the threads will run the same line of code. So they're all going to go for the lock. Whoever gets there first will be able to use the data first, and the other ones will have to wait because they don't have the lock, so they're just waiting there because the code blocks it. They get blocked by the mutex, and eventually when the mutex is unlocked again, another thread can go and grab it. So yep, great job, guys. Take a look at the leaderboard, and we'll get back to the lecture. All right. So let's jump back to where we were. So yeah, just a recap of the two important mutex rules: that you must attempt to acquire the lock before using the data. And secondly, when you finish using the data that the mutex protects, you have to unlock the mutex so other threads can acquire the lock. Because of like the complexity that comes with multi-threaded programming, it's often difficult to follow these rules, but Rust helps us to get past on the complexity and helps us to prevent deadlocking. And we're going to talk about that now. So let's look at this code here for a simple mutex. So this is a single-threaded program. We're not spawning any new threads, but we are going to use a mutex here. It is a little different to what you might imagine because Rust does a little differently than other languages, but I'm going to talk through it. So firstly, we create a new mutex type using the new function. So our mutex also holds this value 5 at the moment when we initialize it. So very important, we're using the new keyword to declare this new mutex, and it's going to be called m. And then to access data inside the mutex, we use the lock method to acquire the lock. So we say let mutable num equal m.lock, and we unwrap it. I'll talk more about this later. And this will block other threads also trying to access the data. Because let's say 2 threads are going for the lock at the same time, whichever thread gets here first will be able to unlock the mutex, do whatever it wants with the data, and the other thread is just going to have to wait at this line here until it can get the mutex. So we can treat the return value, named num in this case, as a mutable reference to the data inside. So num isn't like its own separate variable, it's just pointing to the value inside the mutex. And we're dereferencing it to allocate values to it or edit it. So if you haven't like put it together already, mutex t is like a smart pointer. Or to be more, because mutex t allows you to have multiple owners to the same thing, which is why it works with multi-threaded programs. To be more accurate, the call to lock returns a smart pointer called mutex guard wrapped in a lock result that we handle with our call to unwrap. So when we call lock, we get mutex guard, which is wrapped in lock result, and then we unwrap it to get the value, which is here in num. So the mutex guard can be dereferenced to point to our data, and we see that here. So when we dereference it, we get the value here. Or we can assign values to it after dereferencing it. And the mutex guard also has a drop implementation that releases the lock once mutex guard drops out of the scope. So if you haven't heard of the drop implementation before, I believe Sammy covered it last lecture. Essentially, this works is how like Rust handles like garbage collection. When a variable or pointer goes out of scope, the drop is called on it so that it releases its resource that's being used. So mutex guard automatically has drop called on it, and that'll also unlock the mutex. So if this seems like a lot of like words, a lot of like complex jargon in there, we have TLDR here. We don't risk forgetting to unlock the mutex because this is done automatically for you. So Rust automatically handles unlocking the mutex by using drop. And therefore, deadlock in Rust is very unlikely. I actually don't think it's possible to deadlock in Rust, which is great. We don't want to deadlock in Rust, although it's a little more complex, like syntactically helps us logically to write cleaner code that is less likely to fail. But unfortunately, use of this kind of format doesn't work in actual multi-threaded code in Rust. So I'm going to talk a little more about that. So what we're going to talk about now is more Rust specific and doesn't really work in other languages. However, to use mutexes between multiple threads, you need to do more than just the code you saw in the previous example. So we have to use the argt smart pointer type. And I'm not going to go too much into like the nitty-gritty stuff about it. All you need to know is that it's an atomically reference counted type. What this means, like only one, it has like single value and it counts, it's like a counter variable. And we use argt for additional thread safety. So this makes our programs thread safe. However, they aren't as fast, so we lose some performance when we use the argt type. But we have to use the argt type because otherwise our multi-threaded code won't compile when we are creating multiple threads in Rust. And no, we only have to use argt for multi-threaded programs because if we're having a single-threaded program and we use argt, we're just losing performance for thread safety, which is not needed because we have just one thread. All right, so let's look at this code here and let's walk through it. So I'm just going to talk about it quickly before we go into the pointers and stuff. But essentially, we're going to create a mutex here. I'm going to create a vector called handles, which will have all our threads. We're going to loop here, clone the counter to our new thread, create the thread, unlock the mutex, increment the number, add this new thread to our handles vector, and then we're going to join at the very end. Okay, so let's go through this like step by step. So we give a value multiple thread safe owners by using the smart pointer argt to create an atomically referenced counted value. This is very similar to before, except we cast it to the arg type. We still use a new keyword within the mutex. Within here, we then spawn 10 threads, and each thread increments our value once. So notice once we dereference this value, because it's mutable, we can edit it. And once it's dereferenced, we can just treat it like a regular variable in Rust. So we spawn a thread and increment within each thread. And we join our threads at the end. So using join synchronizes all our threads because you know that we don't know when these threads will finish. Because although we're spawning 10 threads, if your computer doesn't have 10 processors, it's not all going to run 10 things at the same time. It'll be like maybe 4 things running at once, and it'll do like each thread once or twice. And then we print our result at the very end. So the reason we have our join up here is because we don't want to like print our result when when some threads are still trying to increment the value. And also if we printed before joining, we'd see print line results being printed like 10 times. And we get our final result, which is 10. So the key thing to note here is that when we use the arg-type function, this makes it thread safe. So now, when we create these threads and we want to use the mutex, we're not going to have issues with multiple owners trying to own the mutex because the arg-type smart pointer allows us to have multiple owners with the mutex. Does that make sense? There's a lot of content there, so if you have any questions, you can drop them in the chat right now. All right, if not, we have, so this is a pretty simple code excerpt, but because all we did here was really increment a variable to 10. And honestly, if we timed this, it probably would take the same amount of time as a single for loop without creating all these threads. But this simple code excerpt can be set up as a template to make more complex multi-threaded programs or functions. Because most of these will have the same feature where we have to create all these threads, do something to data within the thread, and then like return that value or print that value. So we can use this example here as a template for more complex multi-threaded programs. All right, and with that, we can go into our next Kahoot. So true or false, when you finish using the data that the mutex protects, you must unlock the mutex so other threads can acquire the lock. Okay, great. So once you guys correct, so when you finish using the data that the mutex protects, you have to unlock the mutex. Because you unlock the mutex, when all the other threads hit that line, they'll lock, and they won't be able to unlock and finish the code. So great. Next ones are more like syntax to see if you're really paying attention. So what keyword do we use to lock the mutex? I really hope you guys get this all correct. There's a big hint in the title. All right, so most of you guys correct again. If we want to lock the mutex, we use the word lock. So the words guard and protect, which are the other options picked, they might seem like good ideas because it is what you're doing. You are like protecting and guarding the data from other threads when you lock it. But unfortunately, the keyword we use is lock, and this is actually pretty. You'll see this in other like languages, like C, for example, where we lock the mutex. So it's just a general like syntactical thing that we use. So what keyword do we use to create a new mutex type? All right, great. So new is the correct answer. As we saw in the code previously, when we want to spawn this new mutex, we use the keyword new. If spawn is correct. When we want to declare a new mutex, we use the new keyword. So great job. Final question. Argt is not thread safe. True or false? The archetype, sorry. All right, so great job, Mrs. Correct again. So RT is thread safe, so this statement is false. As we know, we use the RT type because it allows our mutex to have multiple owners and makes it thread safe too. So when we have multiple threads access the mutex at the same time, we aren't violating any issues with Rust. So just for next, we can look at the leaderboard. So great job, number one, for getting all of them correct. Awesome, so great job, everyone. And I'm just gonna close this. All right, yeah. So I'm just gonna look at if we look at code one last time, the biggest thing I want to like drive home today is that our mutex protects our data. So although we're using a shared memory, which we said previously in the last lecture was not good, a shared memory is actually very doable when we have mutexes because it allows us to prevent other users from accessing the data. Mutexes do add some more complexity because we have to lock and unlock them. Thankfully in Rust we don't have to deal with the unlocking step, just the locking. But this is very typical of other languages like C and C++, where you can have parallel programming, but you have to have shared memory. Therefore, using mutexes helps us allows our programs to work the way we want it to and not leave it up to chance for how like this, the scheduler allocates time to the threads. So finally, I want to talk about uses for concurrency. So to start off, concurrency really isn't limited to specific group tasks. It optimizes certain tasks. And honestly, anything you can do concurrently, you can do linearly too. But concurrency does help us in many ways because it speeds up tasks that would otherwise take a long time. Is there EC for the Kahoot? Sure, why not? Last lecture, they're tricky concepts, so yeah, let's have EC. So what concurrency actually does is increases a program's throughput. So what do I mean by throughput is, it allows the number of tasks completed in a given time to increase proportionally to the number of processors. So when you're writing code normally like in a single thread, it's often only being run by one processor. And that really isn't maximizing the use of your hardware. But if you have multiple concurrent programs, then more of your processors will be used at the same time. So the more processors you have, the more throughput you can have because more tasks can be done because all the different processors can do different things. And this can improve overall program structure because some tasks are just designed to be like concurrent. So yeah, if you have a problem that is just very, very concurrent, like it's like for an example, like a real life example would be like baking cookies. If you're gonna do each task like getting your ingredients, mixing them up, putting them in the pan, putting in the oven, one by one each time in a row, if you have to make 4 cakes, it's gonna take a very long time. But if we do them concurrently and we have like one person doing each thing, then we're going to increase the throughput overall for this task. And I guess finally, this usually utilizes hardware better than non-concurrent programs because when you only have one process running at the same time, you're just wasting the other 4 that you spent. Like most computers are quad core, a lot of them 8 cores, and if you're not using all these cores, then you're not maximizing the use of the hardware built into your computer. And with that, that's everything we wanted to cover today for concurrency. And thank you all for a fantastic semester. I hope you guys enjoyed the course, thought it was useful, learned something. And if you're interested in running for any positions on core staff, specifically like project manager, we'll be sending applications soon, so keep an eye on Piazza for that. And yeah, with that, that's everything I wanted to cover. You're free to leave. Hope you have a wonderful weekend. And thank you for coming to the last lecture.